Good. So good afternoon, everybody. So it's my pleasure to introduce the next lecture by Frank Vallentin from the University of Cologne. And Frank also doesn't need an introduction. So I prefer to leave you the whole hour to tell us about your work, Frank. So,
okay, thank you. Yeah. Thanks, Monique. Yeah, so I want to talk about a project which is running since basically 1.5 years, together with David Castro Silva, Fernando Oliveira Filho, and Lucas Slot. And we were discussing a lot via Zoom, of course, about a recursive Lovász Theta number for hypergraphs. So I realized that this is going to be my first talk I ever gave about hypergraphs. So if something looks very strange to you and you don't understand things, then mainly this will be the reason that I don't talk the hypergraph language properly. And if you get confused, then please ask questions immediately so that we can rectify things. All right, so the talk will be subdivided essentially into 2 parts. So the first part will be that I will motivate and define our new recursive Lovász Theta number for hypergraphs. That's really the first half. In the second half, I want to show you some examples. And the examples have a lot of symmetries. And for this reason, we will talk about how we can use symmetry reduction techniques in order to work with these examples. But first of all, let's start with the definition and the motivation for this recursive Lovász Theta number. Okay, so some hypergraph language. So I want to introduce the hypergraph independence number. So for this, I will consider special hypergraphs. So these are R-uniform hypergraphs, H. So V is the vertex set and E is the edge set. And the edge set consists out of hyperedges, and it's R-uniform in the sense that every edge contains exactly R vertices. So if R is equal to 2, then we just have a normal graph, but now we allow a larger R. Okay, and then we will talk about independent sets. And independent sets in H is a subset of the vertices so that no edge is contained in I. Or in formulas, for every edge, for every hyperedge you have, that E intersected with the independent set is the empty set. And then, of course, we want to find the independence number of H or the stability number of H. So that's the largest cardinality an independent set can have in H. So I think it's good to see.
No, sorry, Frank. Yeah. Can I just ask a stupid question? So you define independent if no edge is contained in I, and then you. So sorry.
Yeah. So edges are subset of the vertices, and I is also subset of the vertices.
So, but isn't it different to say an edge is no edge is contained in I, and the second line seems to say every edge is disjoint from I.
Ah, okay. Yeah, maybe forget this. I mean, just.
Okay, good. So, thanks.
Yeah, I see. Yeah. Okay.
So we should remember no edge is contained in I.
No edge is contained in I, and you shouldn't take a look at the formula. Exactly. Thanks. So maybe also it's worthwhile to look at an example, and then I think things become even clearer, I hope. Okay, so the example will be that we will model the problem of a graph without triangles. So it's one of the most basic problems in extremal graph theory, and it comes with the name of Mantel theorem. But let's model this thing as a hypergraph problem. Doesn't want to continue anymore. Okay, like this. Okay, so what do? We look at the hypergraph Hn. So it's indexed by natural numbers, vertex set Vn and edge set En. So the vertex set will be all edges of the complete graph, Kn. I will show you a picture, then it becomes also clearer. And then I want to have an hyperedge between these three vertices. If x, y, z form a triangle in Kn, I think it's better to look at this picture here. So what do we have? So we have 6 vertices, and every vertex is an edge of Kn. And here we talk about K4. So we have 6 edges in total, so 6 vertices for the hypergraph. And then I draw a hyperedge. For example, this light blue hyperedge. I hope you can see it. If I have that these 3 edges, they form a triangle in K4. So these 3 edges, as you see, they form a triangle in K4, and therefore they form a hyperedge. And then you see that in total I also have 4 hyperedges in this hypergraph. Whenever you have a triangle in K4, I draw a hyperedge. And then the question is to find the independence number of this hypergraph, or in other words, to find a subset of the edges of the complete graph of maximal size so that you don't have a triangle. And for example, you can see that if you take this vertex here, this vertex here, this vertex here, and this vertex here, that these 4 vertices, they form an independent set. So you don't find an edge, a hyperedge, which contains all, which is contained in these 4 vertices. Therefore, for example, this edge and this edge, you have a hyperedge containing both, but then if you take this one, it's not there anymore. Okay, and then you can convince yourself in a few seconds, basically, once you understand this picture, that the independence number of this hypergraph is equal to 4. Whenever you add another vertex here, then you will always have that the hyperedge is contained in the vertex set. Yeah, I hope that this example now makes the definition more clear. If not, then please ask questions right now. All right, so we have a hypergraph. We have the independence number of the hypergraph, and we need also some more hypergraph definitions. One definition we will use will be the complementary hypergraph, H bar. So what we do there is that we basically invert the edge set. So the edge set of the complementary graph is all possible edges, or all non-edges, all are non-edges which all non-edges of the hypergraph H. So all subsets of V finality R without E. So it's very similar to the complementary graph when R is equal to 2, but now we just do it for arbitrary R. Then a generalization of the independence number when we introduce weights. So what we do is we introduce a weight function on the vertex set, and then the weighted independence number is not taking the cardinality of an independent set, but it's simply taking the maximal weight of the independent sets, where the weight of an independent set is simply the sum of the weight of the vertices. Another definition, also like in the graph case, is a chromatic number. The chromatic number of the hypergraph is a minimal k, so that there is the partition of the vertex set into k independent subsets. Exactly the same definition as for graphs. And another definition which we also need, but not really neat, but I think it's interesting to look at, is the fractional weighted chromatic number chi star h of w. So that's a solution of some linear optimization problem. So that's the minimum value of lambda 1 plus and so on lambda k, where lambda 1 up to lambda k are the parameters, the variables of the linear program. Then the lambda 1 up to lambda k, there should be non-negative numbers. And then I want to have that there are independent sets, I1 up to ik, so that this sum lambda 1 characteristic function of the set I1 plus and so on plus lambda k characteristic function of the subset ik is equal to the weight function. Yeah, that's a fractional weighted chromatic number. And if you imagine that you only allow lambda 1 up to lambda k to be 0, 1, and if you imagine that w is equal to constant 1, then you model exactly the chromatic number. But now it's in a sense a relaxation. So therefore we allow lambda 1 up to lambda k to be fractional, or be non-negative, and it's weighted. So instead of having a 1 here for w, we allow arbitrary w. And then there is a relation between alpha and chi. First of all, the weighted independence number is less or equal than the weighted fractional chromatic number of the complementary graph. And by the argument I just gave, the fractional weighted chromatic number where the weight function is constant 1 is at most the chromatic number of the complementary graph. Okay, so we have relations between alpha, chi star, and chi. Okay, but all these parameters are known to be NP hard. So it's NP hard to determine alpha, chi star, and chi. That's even true for the easy, in a sense, graph case. So when r is equal to 2. And for hypergraphs, things are not becoming easier. So these problems are all NP hard. Good, but then we know that for the graph case, there is a Lovász theta number, which by the sandwich theorem is sandwiched between alpha and chi star. So the theta number, which I will define in a moment, is an upper bound for alpha and a lower bound for chi star. And the good thing is that you can compute the theta number in polynomial time using semi-definite programming. Yeah, the semi-definite program which is behind the Lovász theta number is as follows. So you have the graph G, that's the input, and then you want to maximize the trace inner product between the matrix J, that's a matrix consisting only out of ones, and the variable matrix F. F is a matrix which is positive semi-definite, and where rows and columns are indexed by the vertex set of the graph. The constraints are that you want to have that the trace of F is equal to 1, and you want to have zeros at positions f, x, y whenever you have an edge in the graph. Yeah, and this theta number of Lovász is useful to bound alpha and chi, or in some situations even to find the exact values of alpha and chi. Yeah, so yesterday David was also discussing this in the context of sphere pendants. Okay, so Lovász theta number for graphs has many different success stories, and I want to recall some of them, also related to David's talk yesterday. So there are some spectacular equality cases where alpha is equal to theta, and this turns out to be in situations where the graph is highly symmetric, or sometimes also infinite graphs, where you can define similar concepts. Yeah, and these equality cases, for example, are by Lovász, when he determines the Shannon capacity of the 5 cycle. Then you have equality cases for the kissing number by Odlyzko, Sloan, and Levenstein. Then you have equality cases for a problem in extremal combinatorics, like Erdős-Corrado theorem on intersecting families of sets by Wilson. Then you have a similar equality case for intersecting families of permutations, Ellis, Friedgut, Pilpel. And then you have the spectacular results on sphere packings, by Biazowska solving the sphere packing problem in dimension 8, and by Kohn, Kumar, Miller, Radchenko, Biazowska solving the sphere packing problem in dimension 24. Yeah, and behind this, you can, in all situations, find a version of the Lovász theta number where you have equality that alpha is equal to theta. Another success story, the success story of asymptotic analysis. So sometimes it's possible to analyze the quality of the theta number when n grows to infinity, some parameter. And this has been done in coding theory a lot, in the framework of the Delta linear programming bound, which is equivalent to the Lovász theta number. And then there are results by McAllis, Rodemich, Rumsey, and Welch, who worked out the asymptotics or bounds for the asymptotics of the theta number for binary codes. And then there is a similar result by Kawatiansky and Levenstein, who proved asymptotic bounds for the theta number for the case of spherical codes or for sphere packings. Also, David was talking about these bounds yesterday. Yeah, another success story is that it's possible to strengthen the Lovász theta number. So if the Lovász theta number is not tight, if it doesn't give an equality case, then there are systematic versions, systematic hierarchies to improve it. These are the LP or SDP hierarchies. Familiar names are Lovász-Schreiber and plus operator, Lasserre hierarchy, Sherrard-Adams hierarchy, and many more. And they have been used to improve the Lovász theta number. Yeah, for example, this has been successfully done by Schreiber in 2005, when he found 3-point bounds for binary codes. This has been extended by Monique in 2007, also for binary codes, but not only doing one level of the hierarchy, but an arbitrary number of the hierarchy. Then together with Christine Bachok, we worked on kissing numbers, 3-point bounds for kissing numbers. And in general, all these strengthenings give usually very good numerical bounds. But the drawback is that the analysis, in the sense of asymptotic analysis, is currently most of it is completely out of reach. Yeah, so for example, David was talking about this yesterday. And also, I think Philippe will talk about this on Friday, when they found an equality case, but it was extremely difficult to have a complete analysis of this equality case. But if some parameter goes to infinity, dimension or so, I don't know any strengthening of the SDP hierarchies or of the Lovász theta number where it was possible to analyze things completely. Good, so this was our idea, our motivation, that we want to continue these stories for hypergraphs. And yeah, for this, we try to come up with some lightweight recursive Lovász theta number for hypergraphs. So we were not aiming to find the strongest hierarchy which is possible, but we wanted to find some hierarchy which is of lightweight in the sense that it will be possible to analyze. And the thing is that coming up with some hierarchy is basically easy. But on the other hand, to find a hierarchy which is useful for asymptotics, that's quite difficult. And our main aim was to have some definition which enables this asymptotic analysis. So we are aiming to find not a complete hierarchy, but some strengthening of the Lovász Theta number, which works for hypergraphs, which is in a sense easy, which is very closely related to the Lovász Theta number for graphs, but then which we can analyze asymptotically if the dimension goes to infinity. Yeah, this is what we try to do. I think this is also a good point for questions or complaints. Or no complaints? Okay, then we can continue. Okay, so we want to find some lightweight Lovász Theta number for hypergraphs. So before we do that, we look at the geometry of the Lovász Theta number for graphs. And the geometry of the Lovász Theta number for graphs is encoded in the theta body of found by Grötsche-Lovász fiber. And they look at a relaxation of the independent set polytope. So the independent set polytope of a graph is the convex hull of all characteristic vectors of independent sets. So that was the starting point. So they want to find a relaxation of this, a body which is a bit bigger. And that's the theta body. And here's the definition of the theta body in the formulation of Lovász fiber from 91, in a paper where they introduced the n+ operator. And the theta body of G looks as follows. So these are all vectors F, which are indexed by the vertex set of the graph. So that there is a matrix F, capital F, where rows and columns are indexed again by the vertex set of the graph. And then from this F, capital F, and the small f, you can construct a larger matrix, a bordered matrix in a sense, where the matrix looks as follows. So it's a matrix where the number of rows and columns is one bigger than the number of vertices in the graph. And the top left corner you have 1. Then the first row and the first column is given by this vector f, which is the element of the theta body. Then the rest is a block, this red block here, which is a matrix capital F. And then on this matrix capital F, you have on the diagonal, again, the vector small f. So this construction of a bordered matrix should be positive semi-definite. And you want to have that you have zeros at positions where you have an edge. Yeah, in a sense, what you're doing here is you write down all feasible solutions of the theta number, but not as such, but by some bordering construction, which makes some proofs easier. But if you don't want to think about the details here, about the bordered construction, you simply should think about that the theta body contains all feasible solutions of the theta number. Okay, so that's theta body. And then there's another polytope, a polytope given by the Clique inequalities. So that's the Clique inequalities polytope, or in combinatorial optimization language, it's the anti-blocker of the Clique polytope, which we call Clique here, which is a bit unfortunate because the Clique polytope should also be called Clique. But okay, the Clique polytope doesn't come up in our research here. So I hope that it doesn't confuse too much if we call the Clique inequalities polytope also by Clique. Okay, so the Clique inequalities polytope consists out of all vectors f between 0 and 1, indexed by the vertex set, so that f satisfies the Clique inequalities. So you sum over all cliques f of x should be at most 1, And this should be true for every independent set in the complementary graph, or in other words, for every clique in G. Yeah, so you have these three bodies: independent set polytope, theta body, and clique, inequalities polytope. And then there's a relation between these things. So I think this I want to call the fundamental properties of the theta body for graphs. So first of all, you have the inclusion relation, that the independent set polytope is contained in the theta body, is contained in the clique inequalities polytope. Then property 2, this is reflected by the corresponding optimization parameters. So if you optimize a weight function W over the independent set polytope, you get alpha GW. Then this is less or equal than doing the same thing over the theta body. Yeah, so the weighted theta number of the graph G with weight W is maximizing the weight function over the theta body. And then this is again less or equal than the fractional chromatic number, or the fractional weighted chromatic number of the complementary graph. So when we maximize the weight function over the clique inequalities polytope. Yeah, so these inclusions here are reflected by the inequalities of the optimization parameters. Okay, so third fundamental property is that the theta body is indeed a convex body, so convex and compact set. And the theta body has a nice inequality description. Namely, these are all vectors f, which are non-negative, so that the inequality f fulfills is that the weight of f is less or equal than the theta number of G with weight function W. And this goes through all possible non-negative weight functions. And of course, one of the inclusions is trivial, but the other one you have to do some work. And last item is that one can optimize over the theta body in polynomial time. Yeah, so these are the fundamental properties of the theta body for graphs. And now the plan is to come up with a definition of a theta body for hypergraphs where these fundamental properties are basically surviving. Okay, so let's do that. So now we come up with some recursive definition of the Lovász theta number for hypergraphs. And we are very much inspired by the n+ operator of Lovász-Schreiber. So if you know the n+ operator, you will see a couple of things which are known to you. It's not exactly the n+ operator, but it's inspired by that. Okay, let's do that. Let's give the recursive definition. So we start with the base case. The base case is here r equal to 1. Yeah, so in the base case r is equal to 1. Then the edge set is contained in the set of vertices. Yeah, so we don't start our base case at normal graphs. We start one below normal graphs. And in this situation, we simply set that the theta body of H is equal to the independent set polytope of H. Yeah, so the independent set polytope, which are defined for graphs, you can also define for arbitrary hypergraphs in a similar way, just by taking the convex hull of characteristic functions of independent sets. And you can do this even for the case r is equal to 1, which is a bit degenerate, but still it works. So that's the base case. So let's look at the recursive step. So now we have r at least 2. And for the recursive step, the link hypergraph of a vertex will play an important role. So the link hypergraph takes a hypergraph we're looking at, looks at it at a vertex, and constructs a new hypergraph out of this data, which is then not no longer R uniform, but it is becoming R minus 1 uniform. Okay, so what's happening? So we get a new hypergraph, HX, where the vertex set is Vx and the set of hyper edges is Ex. So what is the set of new vertices? Vx, the set of vertices are all vertices in the original hypergraph, so that X and Y together are contained in some edge. So we select some of the vertices, not all of those. We only select those where we have a common edge, where X and Y are lying in some common edge. And then the edge set will be all subset of the vertices of size R minus 1, so that you can enlarge your edge by X and you become an edge in the original hypergraph. Okay, so this usually requires some time to digest. So let's look at the example. And here's the example of the hypergraph we discussed at the beginning again. So here's the hypergraph. Now I want to find the link of this vertex here. So what I'm doing, I take all edges which are containing this vertex here. And these are these two edges, this hyper edge and this hyper edge. Then to construct the link, I simply delete this vertex. So then I have these four vertices left. And then I connect the vertices, like this one with this one, because if I add the original vertex X to it, then I get a hyper edge. Yeah, so going from this hypergraph, I take the link of this vertex here. I get now a two uniform hypergraph, which is in this situation just a graph. The graph on these four vertices, they have an edge here, an edge there. Yeah, so this will be an important construction in the definition of our recursive Lovász Theta number for hypergraphs, taking the link. Questions about this construction? Okay, so once we have the construction, we can define the theta body of a hypergraph. So here's the definition of the theta body of the hypergraph. So again, these are all vectors f in R to the v, as before. So they exist a matrix f. Again, rows and columns are indexed by the vertex set. Then this bordered matrix is positive semi-definite, just as before. But now we do something new, something different. So we give some constraints of this red matrix F. And what we are doing is, for every x in V, we take a look at the construction Fx of Vx. So what's happening here is we take the column of F, which is indexed by x, and we restrict, in this column, we restrict the vector to the vertex set Vx. Yeah, so this is an element in R to the Vx. And this vector should be contained in the theta body of the link hypergraph Hx, which is R minus 1 uniform. And we multiply this theta body with the diagonal constant Fxx. And if you know the n plus operator, this construction looks very familiar to you because it's one of the two constraints which you use when defining n plus. Here's something else for the n plus operator, but now because we're dealing with hypergraphs, it makes sense to take a look at the links. So it makes sense to restrict ourselves to vertices like in Vx. Okay, so that's our recursive definition of the Lovász theta number for hypergraphs.
Can I ask a question, Frank?
Of course, yeah, please.
So in the definition of the n plus operator, there would be also a condition saying that the zeros column minus the x column belongs to somewhere. So you don't have such a thing here.
We don't use this here now.
Okay.
And the motivation is we want to have it as simple as possible in order to be to make some analytic bounds at the end.
Okay, but you could have used it.
You could have this. You could do this, of course.
Okay.
But then we don't know exactly how to continue to work with that. We
Okay.
could make the definition. We could also come up with some properties, but then the asymptotics wouldn't work as nicely.
Okay, thank you.
All right, so that's the definition. Yeah, first sanity check. So what happens in the case r is equal to 2? So in the normal graph case. Then it turns out that in the normal graph case, we are going to recover the original Lovász theta, the theta body again. Maybe because of time reasons, I don't go through this. Just believe me that if r is equal to 2 and we unfold the definition we are just discussing, then you end up with the original theta body again. So then the first sanity check is okay, because then we didn't define anything new in the case of graphs. Second sanity check. We want to see that the independent set polytope of H is contained in the theta body of H. There should be H here. So this was the first fundamental property. And here's a small proof. I think I also go over this because of time reasons. You just do it. If you saw this definition the first time, then I think it makes sense. And if you want to work with this, it makes sense to do this proof once, because then you get familiar with the concept. Yeah, but this is also going to work. So the independent set polytope of H is contained in the theta body of H. Last thing, last sanity check, the fundamental properties. Here are the 4 fundamental properties we were just discussing about graphs. And now we see that's basically the same holds true for hypergraphs if we use our definition. So the independent set polytope of H is contained in the theta body of H, is contained in the Clique inequality polytope of H. But here there's a small difference, or some difference to the graph case. Because if we talk about cliques in H, and if we talk about R-uniform hypergraphs, then the Clique inequalities shouldn't have a 1 here on the right-hand side, but they should have an r minus 1 on the right-hand side. Simply because we talk about R-uniform hypergraphs.
But did you say how you define a clique, Frank?
The clique is an independent set in the complementary graph.
Okay.
It's going to be the same thing. Yeah, so when r is equal to 2, then we have the 1 as before, but if r is larger than 2, we have to modify the Clique inequality polytope again, slightly. Okay, good. So this we have to do. Then we have inequalities between the optimization parameters, where here's a small difference again, that we have to squeeze an r minus 1 in front of the chi star, simply because in the Clique inequalities, we also have the r minus 1. But in all other things just go through, just going from D to H. So the theta body is a convex body. The theta body has some inequality description, and you can optimize over the theta body in polynomial time. we are basically using the ellipsoid method. Okay. So now we have the theta body, so we have some tool to work with. And now we want to look at symmetry reduction techniques and examples, so to demonstrate that the theta body we are just defining is also useful in different contexts. Okay, so we do symmetry reduction basically in 3 steps. So symmetry reduction step 1 is when we talk about vertex transitive graphs. So suppose you have a group gamma, subset of the automorphism group of H, which acts vertex transitively on H. So every vertex is in a sense equivalent. Then we can simplify the computation of the theta number a little bit. So then for any z in the vertex set, I can compute the theta number of H. Or what this meant is the theta number of H with the constant weight 1 by the following semi-definite program. So what I want to do is I want to maximize the trace inner product between J and F, where I have a normalization factor of 1 divided by the number of vertices. Then F should be a positive semi-definite matrix, which should be gamma invariant. Yeah, so simultaneous operation in rows and columns by gamma should leave F invariant. Then on the diagonal at Z, I want to have a constant 1. And I want to have that Fz of Bz of the link should be in the theta body of the link of Hz. And because the group acts vertex transitively, I have only one constraint and not a constraint for every vertex. Yeah, so this simplifies, first of all, the computation of theta a bit. And secondly, you see that this definition of theta is very close to the original definition of theta for graphs. So there are a couple of small differences. One difference is a different normalization, but it's just more convenient to work with. And secondly, this condition here is the replacement of the condition that fxy is equal to 0 if x and y form an edge. But because we work with hypergraphs, of course, we need something else. And something else is really talking about the links and then having that this vector is in the theta body of the link hypergraph Hz. Okay, so small proof. Maybe I don't give all the details, but maybe I give you just a hint for the main arguments. So the first thing we realize is that because we have the vertex transitive action, we can assume without loss of generality that our vector f, which determines the border of the matrix, is a multiple of the all1 vector, because every vertex is the same. So that's one simplification. Then second simplification is here. So here you have the matrix with a border. But now, because the vector f is so simple, we can replace this PSD-ness condition by some sure complement argument so that we can get rid of the border condition. And then because, last argument I want to sketch, because we have a vertex transitive action, we see that the all1 vector is an eigenvector. And because of this, we can get rid of the border and we can get rid of the lambda here. And then we get a slightly simpler formulation of the theta number. So that's the first part of our symmetry reduction. Second item of symmetry reduction is when we even have more symmetries. So suppose we have a vertex transitive action on H, and suppose also that the stabilizer of the link is also vertex transitive. then we can simplify the computation of the theta number even more. So what we're going to do is, so we simplify the condition that this vector lies in the theta body. We simplify this condition by saying this one here, this inequality here, that's a sum over all vertices x in the vertex set of the link graph of fz, x is at most the theta number of the link graph hz. Yeah, so this inequality is a replacement now for what we had before, that the vector lies in the theta body of the link graph. So this is just an inequality, and if we are able to compute the theta of hz by some analytic means, this simplifies the computation of theta h. But for this, we need that the stabilizer x vertex transitive on the link graph. Yeah, small arguments, basically the same as before. So we have the link graph hz. Then if a vector A lies in the link, in the theta body of the link hypergraph, then by the third property we have that WTA is less or equal than theta number of HZW for all W's. And because now we have a vertex transitivity on the link graph, I can assume without loss of generality that this W is constant. And then if this is constant, being in the theta body is simply fulfilling one inequality. Okay, that's symmetry reduction part. And in our situations, we will have that that we have such a strong group which acts vertex transitively on H, but also the stabilizer acts vertex transitively on the link. Okay, so let's apply this. And I want to apply it to three different examples. The first example is a graph without triangle. So this theorem of Mantel, starting point for extreme graph theory. Again, so Hn is a hypergraph where the vertices are the edges of the complete graph. I have edges between triangles in Kn. Okay, so here is again the construction of the link. Then I see that the permutation group Sn is acting transitively on En. So all edges are the same in the graph of Kn. Good, so that means that we can apply the lemma we just had. Here is the formulation of the lemma we just had. And then we have to compute the theta number of the link graph. But if you look at the theta number of the link graph, and if you look at the link graph itself, in this example, this is just a matching. And this is also true in general if n is larger. And then the theta number of this matching graph is equal to the independence number, and this in this setting is just n minus 2. So we can compute, in this situation, we know what the theta number of the link graph is, n minus 2. Without doing any computations, it's just by easy theory about the theta number. Yeah, it's a bipartite graph, and then in the bipartite graph, the theta number is equal to the independence number. All right, so we can compute this. Next thing is that the action of Sn partitions Vn times Vn into 3 orbits, into the diagonal orbit, into the orbit where x and y intersect at a vertex, and into an orbit where x and y don't intersect at the vertex. So these 3 orbits, and this, if you know association schemes a bit, then this smells, and in fact it is the Johnson scheme Jn2. And yeah, here is the graph which corresponds to the orbit O1. What's called the triangle graph J42. All right, so that means because we can partition the orbits, we can partition Vn times Vn into three orbits. So that means that we may assume that the matrix F we are trying to find in the optimization problem in the theta number is a linear combination of the matrices A0, A1, A2, and AI are the corresponding 0, 1 matrices defined by the orbits. So we have A0 plus alpha A1 plus beta A2. So we don't have a coefficient in front of A0 because of the normalization constraint that the diagonal is equal to 1. Then, by theory of association schemes, we know that the AIs compute pairwise, meaning that we have a common system of eigenvectors, meaning that computing the theta number is an LP linear program in the variables alpha beta. And then it's easy to solve and to see at the end that the theta number of Hn is exactly n squared divided by 4. So in this setting, we can compute the theta number of Hn exactly for arbitrary n. And in fact, what it applies that no triangle phi graph on n vertices has more than floor n squared divided by 4 edges. And if you analyze things a bit more carefully, you see that equality you have exactly for complete bipartite graphs, where both sides of the bipartition are basically of equal size. And historically, that's one of the starting points of extremal graph theory, and then theorem of Turan and so on are generalizations of this fact. But this is just an illustration of our technique, and it's going to work in these situations. Okay, so then example 2, something new, which couldn't be done before. So we look at triangle avoiding sets on the Boolean cube. So what's happening here? So we look at the hypergraph indexed by n and m. First of all, we look at the Boolean cube. So the vertex set of the Boolean cube are all binary strings of length n. And then I have a hypergraph, a hyperedge between x, y, and z. If the Hamming distance between x and y is equal to the Hamming distance between x and z is equal to the Hamming distance between y and z, which is equal to m. M is also a parameter of this graph. And we want to find independent sets in this Boolean cube. So that's a problem which is interesting in extremal combinatorics in Ramsey theory. Then we can use our lemma which we had before to compute the theta number. For this, we have to understand a bit the automorphism group of this graph. And this is a well-known guy, I would say. So this gamma, the automorphism group of this hypergraph, is generated by permutations and by switches 0, 1. So it's a group of order 2 to the n times n factorial. And now we do symmetry reduction part 3. So we're going to parameterize all gamma invariant f's using some harmonic analysis. So by techniques Lucas was looking at this morning. And then it's a fact that some gamma invariant function f is positive semi-definite if and only if you can write it down in terms of some Kraftschuk polynomial expansion, where the corresponding f case, the corresponding summands are non-negative. So this gives us a complete parameterization of all positive semi-definite gamma invariant matrices. Then the link hypergraph we have to study, and the link hypergraph we study at the origin. So then the link hypergraph has vertices, all binary strings which are at Hamming distance m from 0. So In other words, all binary strings of weight, Hamming weight m. And we have an edge between those if and only if the Hamming distance is equal to m. Yeah, so people who know association schemes, then behind the hypergraph, we have the Hamming scheme, and behind the link hypergraph, we have the Johnson scheme. Then the group of automorphisms of the link hypergraph is now simply the group of all permutations. And now we again parameterize all gamma prime invariant f primes, again by harmonic analysis. And that's going to be very similar to the situation which we had before, about the Kraft-Tritt polynomials, but now instead of having Kraft-Tritt polynomials, we have Hahn polynomials. So that's another family of discrete orthogonal polynomials. All right, so once we have this data, it is possible to compute the theta number of this graph exactly. And here's a statement. So the theta number of the graph H and M divided by 2 to the n is equal to 1 minus 1 divided by 1 minus m and m times 1 minus n and m. And these two numbers are parameters which come from the Kraft-Tritt polynomials or the Hahn polynomials. And what they are simply the minimizers of the Kraft-Tritt polynomials at m when I go over all possible degrees. And similarly, for n, I do the same, but I replace the Kraft-Tritt polynomials by Hahn polynomials. Yeah, so we have a complete expression in terms of these two minima. And if you do some plots, if you do some computations, for example, if the distance which is interesting to us is n divided by 3 or n divided by 4, we see that there is some exponential density decay of the theta number divided by 2 to the n. And that's interesting because of the relations to extremal combinatorics and to Ramsey theory. Now, we don't have a proof yet that this is really exponential decay, but we have, I think, rather strong numerical evidence. Right, last thing I want to do, and it's very similar to the second example, I want to look at simplex avoiding sets in Euclidean space, where the main difference is that we transfer the theory which we just had for finite hypergraphs to infinite geometric hypergraphs. So we can do it for simplex avoiding sets, not only for triangle avoiding sets, as we discussed for the Boolean cube, but because of time reasons and because of notation, I only want to look at triangle avoiding sets. So here, the infinite geometric hypergraph is as follows. We have all vertices are points in the Euclidean space, and I have a hyper edge between 3 points if they form a triangle where the side length is equal to 1. So that's the infinite geometric hypergraph we want to take a look at. We want to compute the theta number of, or the independence number of. Then we have a version of the theta number for infinite geometric hypergraphs, which looks like here. So it's very similar to what we had for the finite setting, but here we have to add some analysis. But I don't want to get to too many details. So I think in 2 minutes I will also finish.
What do you mean by independence number of this graph?
So I look at independent sets, and I want to find the largest independent set of this graph. But of course, what does it mean? Yeah, we have to define this, and for this we define the upper density of the sets. Yeah, so we look at the measurable independent sets, and we compute the density of these sets. Yeah,
Thank you.
We take this limit here. This limit models to compute the upper density. Okay, so we have this optimization problem, and we can solve it, again, using a third step, symmetry reduction, when we look at invariant f's, and we parameterize them by harmonic analysis. What we also have to discuss for 2 seconds is the link hypergraph. So the link hypergraph at the vertex 0 is simply the unit sphere. And I have points which are adjacent whenever they have distance 1. So that's the link hypergraph. And once I have set up all this, I get the theorem which is very similar to the one which I had for the Boolean cube. So the theta number of Hn is 1 minus 1 divided by 1 minus mn times 1 minus nm. And again, these parameters mn and nm are a minima of, say, special functions which are coming from the symmetry of the situation. So the mn is coming from Bessel functions. So here I look at the symmetry of Rn. And the other parameter, nn, comes from orthogonal polynomials. It comes from Jacobi, Gigwa, or ultra-spherical polynomials. So the polynomials also Lucas and Monique discussed this morning. And we have to find the minimum of evaluations of pk at a half, where k goes through all the degrees. Yeah, so in this situation, the bound looks exactly as the one as we had before. We just have to replace the minima by the corresponding special functions, which are defined by the symmetry of the situation. And then we did some not so easy work to see how this bound behaves when n goes to infinity by some asymptotic analysis. And we saw that this bound also drops down exponentially fast by this bound here. And it turned out that it improved some bounds in the literature on Euclidean Ramsey theory. Good. So if you want to see the details, I give you 2 references. So there's one paper where we discuss the Lovász theta number for simplex avoiding sets. So this is already out and is to appear. And the other one about the theta number, the theta body is in preparation. And with this, I want to end. Yeah, thanks for listening.
Thanks a lot, Frank, for the very nice lecture. Are there questions?
Yeah, I have a question. If I,
Of course.
So I think there's several ways of defining perfect hypergraphs. Do you know if one of them is, if for one of them this theta number is sharp? Or...
Yeah, I was fearing to hear this question. I think, yeah, we did investigate this, but I am a bit pessimistic that any perfect is making sense here.
Okay.
But I think it's worthwhile to take a look. But as I said, I'm a bit pessimistic that we have a useful concept here of perfectness.
Okay, yeah, thank you.
May I ask a question, Frank?
Please, please.
So, is this the first time that there is a definition of the theta number for hypergraphs? Or
I think so.
okay, okay. Oh, nice.
I think so.
Okay.
I mean, it's a bit made up because, I mean, as you discussed also before, that we can, in the n plus operator, we could also have the other constraint.
Yes, yes.
So it's not the most natural definition, maybe. But on the other hand, it makes sense and it gives nice formulas.
Yeah, yeah, sure. And you find again in the case r equal to, you fall on your feet. So
exactly, you find the Lovász theta number again. Yeah.
And would it be possible? Did you try to express the original problem as a polynomial optimization problem, or does it make any sense?
Yeah, we tried.
And then the basic relaxation doesn't give you this definition of theta.
No, this gives us something else. Exactly. And we tried a bit to work with that, but we were not able to prove anything analytically. So we thought, well, this is too complicated. So let's find maybe the easiest version of a theta number, which gives results.
Okay, so did it give you a stronger bound maybe than what you now do with this? So this is.
Yeah, I think we even have a proof that.
Is it stronger?
It is stronger. Yeah.
Okay, okay.
But okay, you have a proof it's stronger, but then you cannot do anything with it.
Yeah, no, I understand, of course. Yeah. Okay. Any other questions?
Sven's? I think your microphone is not on, Sven.
Oh, yeah. Do you hear me?
Yes, now I hear you.
Okay. Yeah. I was thinking maybe about a possible application. So the triference problem of Kerner, which asks for the the maximum number of vectors in F3 to the n, a maximum set of vectors in F3 to the n, such that for any 3 vectors there is a coordinate where you have 0, 1, 2, so where they all differ parallels. And it's already open for several decades if you can if the upper bound is strictly smaller than 1.5 to the n asymptotically. So maybe this, because you can also do this in this hypergraph framework. It's basically the independence number of a hypergraph. Maybe your techniques apply there also. I don't know.
We didn't try, and I hear the problem for the first time, so thanks.
Yeah, I heard it 2 years ago from Dion.
Yeah. I think the problem could be, we have to investigate that, I mean, in our situation, the link is already extremely well understood and very nice. I don't know if this is the situation here. I mean, if the link is meaningful and has a lot of structure, I think then our techniques have a chance. If the link is, in a sense, trivial, then our techniques don't have a chance. So it's really about the link.
Okay. Well, interesting. Thank you for the nice talk.
Thanks. I think I saw in the chat by Fernando something.
Fernando should speak up then.
I think he doesn't have a microphone.
So you can read the chat, or shall I?
No, I don't see it. I just saw
Okay,
a
wait a
pop-up
second.
message.
Just an observation to Monique's question. It is not clear how to introduce the 1 minus f of xx constraints to n plus. To see this, you have to look at the proof that the independent set polytope of H is a subset of the theta body of H. Don't know if I decipher it, but
Yeah.
we tried to use these constraints to n plus, but it was wrong. So it stays a bit mysterious, everything.
Yeah. I think sometimes it's easier to speak instead of to write.
So any other questions?
Hi Frank. In this talk, at least, you only mentioned regular hypergraphs, but in general, you can allow different edge sizes. Does everything still work out? Or do some of the nice properties break? Because I assume the definition should generalize.
Yeah, I think the definition generalizes. Also, I think the fundamental properties also generalize. But then the symmetries and so on, they don't generalize. But you're right. I mean, we could open this a bit more. But the question is again, I mean, does it make sense? And I think our definition makes sense if the link is interesting and has a lot of structure. But if you have not even a uniform hypergraph, the links will be all different and it will be rather messy, I think, at the end. But you're right. I mean, the basic definition makes sense.
Okay, good. Thank you.
Okay, so as it seems no more questions, so let's thank Frank again for his very nice, very clear lecture. Thanks a lot, Frank.